Hello class, today we're going to focus on the unit circle. And you might say, well, how are we going to do that? Well, the best way I know how is to, well, let's just use a real life example. So we're going to use a Ferris wheel, because why not? So you'll see the Ferris wheel I have drawn below, and you might say, wow, that actually looks decent. Yes, you're correct. It did take a while. So, let's just assume that we're riding on this Ferris wheel and that it is moving in this motion here, which we'll refer to as counterclockwise with this abbreviation of CCW. And we're just going to say we start, let's say over in this position, we're sitting on the Ferris wheel waiting our moment to start moving around. As time progresses, you'll notice that we start moving upwards and ride this Ferris wheel higher, and we get to the highest point and we start going lower. And we start getting to a lowest point and we keep going. So you'll say that these positions we'll call 1, 2, 3, and 4 are all changing, and it's based on time. As in, as time progresses, you're going to end up starting from this position, rotating along here, getting to this position as time 2, keep going, rotating to here, getting to time 3, and then time 4. Notice things that are similar about all these positions. And I'll start off by saying, if you actually look at this, that the distance to the center of this point of the Ferris wheel is the same for points 1, 2, 3, and 4, meaning that the distance to the center, the radius, is constant. So again, this is a circular path that we're going on or along the Ferris wheel. So let's draw a quick diagram from position 1 to position 2. And notice in this case, I had the initial ray and then the terminal ray and some angle theta here for this change in position. Now we should note that from 1 to 2 we go along this path having an arc measure, and also that's really interesting along this is that, again, since the radius remains the same, the only thing changing is your theta. So with that fresh thought in your mind, I want you to take a moment and really pause the video to answer this following question. So in example 1, how does the vertical position of the person change with respect to time? So focusing on just the vertical motion of the person, how does it change with respect to time? So I'm not exactly sure what you may have written, but I have an idea of, let's just take a guess. Let's say you may have said it's linear, or it's a constant rate. Now I'm going to tell you that's not exactly true, because if we're actually looking at this position of the person, we're going upwards, but we're not going up directly, we're actually following along this curve. And then going to the top, and then we kind of slow down, stopping at the top vertically, and then we go back down. If we were to look at that just along a y-axis, and I'm going to label that over here, just overlay this. So this is your x, and this is going to be your y. Not the easiest thing to see, I suppose, but it'll do the job just for now. Is to say that along the y-axis, if we're just looking at the y position, you start here at time 1, looking at your initial position, and as it gets to time 2, we're about here. Okay, so now we start getting to 3, we get to this point approximately here. And 4, we start going all the way beyond the x-axis, way down here. I urge you that if you did not understand this last part of the y-axis, focusing on the y-axis motion, and you didn't follow the points 1, 2, 3 and how they translate to the y-axis motion, I urge you to replay the last part at least one more time. So let's get back to actually answering the question, and the answer isn't linear, nor is it exponential, nor is it logarithmic. I know a few of you will jump to that. It's actually a sine function, and we typically write that as sine and hopefully you know how to spell function, maybe I do. And we can denote that simply with respect to sine theta. Notice in this case that I actually abbreviated sine here. Like I said, mathematicians are lazy, and we decided, no E, we don't need an E. And we're just leaving it as sin theta. So large takeaways from this is first that sine is a trig function. We'll talk more about that later, but it's specifically used for the unit circle. And the unit circle here has a focus on sine theta. So the parameter here for sine is theta, as in sine changes based on your radian or your angle measure. So that is your focus here. Well, what is that equal to? Because always we have to have something equal to something, right? Well, in this case, we're going to say it's your y position divided by your radius. That's one way of writing it. Another way, if you wanted to rewrite the equation, is to say if you're looking at just the y position, aka just along the y-axis, we can say that here that it's sine theta multiplied by the radius will give you your y position. So with that work done, let's move on to another question. And for this question, example 2, how does the horizontal position of the person change with respect to time? So feel free to pause and take a moment to think how you might try this. Now, if you said linear, okay, now you're just not paying attention. Really go back to example 1 and go through this part of the video and review that portion. But the major part I want to state is it's not going to be linear. It's actually going to be another trig function. And in this case, it's actually going to be your cosine function. We're going to write cosine with the full way of writing it with C-O-S-I-N-E, but typically we actually refer to it as C-O-S, and again with the parameter of theta here as your angle measure. And what is this equal to? Well, this is going to be your x over r, referring to your x position rather than your y position. And you might say, well, how's that true? Whoa, that's not possible. But the thing is, as they're going up, as this person's going up and doing the counterclockwise motion, notice if we look just at the x-axis, I'm going to follow this along, and as time progresses, as the angle changes, we're moving actually towards the left. And eventually, when we're at the top of the coaster, we're actually here at the crosshair. Keep going. And we're going to be eventually over here. And then so on and so forth. As we start going lower, we actually have only a translation to the right along your x-axis. So basically, you have a starting from here, left and right motion that has a speed change that is not constant. So it can't just be a linear function. So as we continue working on this, we're going to say another way of writing it again is, I'm going to write this in parentheses, cosine theta multiplied by r equals x, and that'll just give you your x position, saying cosine theta, cosine of your angle measure, times the radius equals your x position. So thank you for watching. I was happy to have you all here today, and I hope to see you all next time. Have a great day.